Mic is yours, Pierre-Antoine.
Thank you very much. Hi, everyone. So, the ambitious title of this presentation is what you always wanted to know about RDF fleet rules. A short word on how the idea of this presentation came up. A few months ago, I ran into a number of issues in different contexts, but all related to RDF fleet rules. So I dug into those issues and made a number of discoveries on RDF fleet rules, things that after 20 plus years working on RDF, I didn't quite know or realize about them. So I thought, well, there's a few things that might be useful also to other people. So I started working on this presentation, and working on it, obviously, I thought of other things, other questions that then I dug into and discovered yet a few more things. So that's all those, all those things that, no, it's still wrong. Okay, sorry about that. So I will first remind a few things that I guess you know that are from the specs, the RDF specification, among others. So what's written down, what's there about RDF fleet rules, and then explore a few consequences of those things in Sparkle, in JSON LD, Shackle, and OWL, and then give a few perspectives on what's in the pipes for RDF fleet rules in the near future. This was meant to be rather interactive. I hoped at some time that I could be present in Sofia to give this presentation. That was unfortunately not possible. So, but feel free. I have the WebEx window visible. If you raise your hand, I'm not sure exactly where that will manifest, but feel free to interrupt and ask questions during the presentation. I was planning on doing a show of hands or stuff like that, but that might be a bit complicated. But again, let's keep this interactive. Don't hesitate to turn on your mic and interrupt me if you feel the need. So a few things that should be known about RDF lit rules. First of all, what is a lit rule? So it's one of the three kind of terms in RDF, besides IRIs and blank nodes. Lit rules are made of 2 or 3 elements. I will mostly focus on the first 2 in this presentation, which are the lexical form of the lit rule, that is the string value of the lit rule, and then the data type IRI, which is, well, an IRI and identifies the data type. The third optional part is the language tag, which is only for one special kind of lit rules. And again, I will mostly not talk about this one in this presentation, except a little bit in the end. That's for the syntax. Okay. Now, the data type IRI is meant to identify a data type, and data types in RDF are actually inherited from the XML schema specification, which defines a data type as made of 3 parts. The lexical space, which is the set of strings that are valid for this data type. The value space, which are the set of things which are represented by this data type, like numbers, dates, whatever. There's no limitation of what the value space could contain. And finally, the lexical to value mapping, or L2V for short, which tells how the strings in the lexical space are correspond to the values in the value space. That's basically what a data type is. Now, how do those data types fit into the semantics of RDF? Because in the end, those terms in the RDF graph are used to represent the values in the value space in the RDF semantics. But before that, sorry, a few examples, okay, of this definition of a data type. So the most simple one is XSD string. The lexical space is the whole set of all possible strings that we can think of. The value space is the exact same set, all possible strings. And the L2V mapping is trivially the identity. So the lexical form of a literal of type XSD string, a literal of type XSD string denotes exactly its lexical form. So nothing really complicated here. Another interesting data type is XSD decimal, which is the basis of many numeric data type in XML schema. The lexical space is the set of strings that match this regular expression. So an optional sign followed by a sequence of number, optionally followed by the decimal point and another sequence of number. Any other string is not valid for this data type. The value space is and I quote, the set of real numbers that can be obtained by multiplying an integer by a non-positive power of 10. That is any real number that has a finite writing in base 10. And the L2V mapping is exactly how you would expect it. So you pass the string, and that gives you a number. An interesting feature of this mapping, contrarily to the one from XSD string, is that it is not injective. Several lexical forms may map to the same value in the value space. For example, 1, 1.0, or 0, 1.000 all map to the same value, which is the number 1. And it's actually common for data types to have non-injective L2V mappings. XSD integer is another popular data type. What not everyone might know is that XSD integer is in the XML schema specification not a primitive type. It's a restriction of XSD decimal. And it's what's funny is that this restriction is defined on the lexical space. It's the set of decimal whose lexical form matches this more restrictive regular expression. And the result, and again, I quote the spec, the result is the standard mathematical concept of the integer numbers. Because obviously, the subset of all decimal values that can be represented with this regular expression correspond exactly to the subset of integers, relative integers. Another data type that I will use in my example is XSD double. The lexical space is defined as any representation that matches the decimal that we saw earlier, optionally followed by the letter E followed by an integer, or alternatively, the 3 special values, infinity, minus infinity, and not a number. The value space is the set of all numbers that can be represented by IEEE double precision 64 bits floating point numbers. So the regular notion of double as you have in most programming languages. And the L2V mapping is again as one would expect. Again, an interesting feature that not everyone might realize is that according to the XML schema specification, the value space of XSD double is disjoint from the value space of XSD decimal. As a matter of fact, all primitive types have disjoint value spaces according to the XML schema specification, meaning that 1 as a double is a different thing than 1 as a decimal. They are different things. Of course, they are mathematically equal, as we will see. Further layers in the stack take care of hiding this technical oddity or counterintuitive feature. But that's one thing. They denote different things in the universe of discourse. Okay, so that's how XML schema defines data types. Of course, RDF is not limited to data types defined in XML schemas. RDF can use any data type defined in any other specs, provided that we have an IRI for this data type. But that's how those very usual data types are defined. Now, how do they fit in the RDF semantics? And for that, we need to come back to how the RDF semantics is defined in a number of layers. We have this for the simple entailment, and de-entailment, and RDF entailment. And we will see how each of those levels handles literals. That's the definition of a simple interpretation, the RDF semantics. I believe that's this is still in the reminded section, but I believe not everyone has dug into the RDF semantic specification. What's important here is the fifth point. So an interpretation, a simple interpretation maps some literals to things in the universe. Okay. From that respect, in simple interpretations, literals do not have any special semantics. The data types here, the special semantics of data types is not taken into account. The only one thing that makes literal the main difference between literals and IRIs in simple interpretations is that all IRIs are supposed to denote something, while some literals are allowed to not denote anything. And that will be important when we take the semantics of data types into account, because as we know, some data types restrict the lexical form of the data type. Like hello world of type XSD integer is not a valid integer. It does not denote anything. It makes any graph containing it inconsistent. So that's why the mapping from literals is partial, okay, to allow this to be taken into account in further layers. But at this point, that's really the only special thing about literals. And data types, the special semantics of data types is not taken into account. The next layer is precisely what brings the data types in the picture. So D interpretations are interpretations where D is a set of so-called recognized data type IRIs. So it's a parameter of the interpretation. Some interpretation might only recognize integers. Other interpretations might recognize, and when I say interpretation, sorry, some implementations, okay, might understand integers but not decimals. Some other interpretation might recognize integers, decimals, and doubles, and so on and so forth. And for all recognized data types, there are constraints on the interpretation that complies with the previous definition. First, the IRI of each data type must actually denote that data type, obviously. And then the mapping of literals must be consistent with the L2V mappings of the recognized data types. So basically, what a D interpretation says is that for the set of data types in D, the set of recognized data types, the interpretation must do exactly what you would expect from the definition of the data type. So the integer whose lexical form is 42 actually denotes the number 42. Finally, when it comes to RDF alone, the last layer is the RDF interpretation. So that's the full semantics of RDF before extensions such as RDF schema, OWL, and so on, is a D interpretation where D must contain at least two data types, which are language string and string. Language strings are those special strings with a language tag, okay? And XSD string is a very simple data type that I presented earlier, where each string is mapped to itself. An interesting thing also of RDF interpretation is that for every IRI ADT in D, so for every recognized data type, all values of this data type are linked with the RDF type relationship to that data type. Which means, I guess an example would be clearer here, which means that the following graph would be a consequence of any RDF graph if only it was valid RDF. It is not valid RDF because I put literals in the subject position, okay? So the integer 42 is of type XSD integer, and the decimal 42.0 is of type XSD decimal. But as you can see, the integer 42 is also of type decimal, because remember, the value space of integer is a subset of the value space of decimals. So actually, those two literals are denoting exactly the same thing. And as such, they are both the same thing, both of type integer and literal. Why is it important to have those consequences in the RDF semantics, since those consequences cannot legally be expressed anyway in RDF? Any idea? well, I don't see him hand raising. So one thing is that this allows us to write in RDFS, in RDF schema, things like that. We are used to say this property, like DBO parent, has range the class DBO person, meaning everything that is the value of DBO parent must have RDF type person. But we are also used to use RDFS range with data types, like birth date has range XSD dates. And actually, we can do that because under the hood, what happens to the values of birth dates is exactly the same as what happens to the values of parents. They are forced to have RDF type XSD dates. Of course, they are literals. Well, they are usually literals. So the triple, this literal has type XSD dates cannot be expressed in RDF. So that's a consequence that cannot be written down in syntactically legal RDF, but that's still a valid consequence. And therefore, range can be used regardless with classes and with data types. So that's basically how literals and data types are defined. What are the consequences in different parts of the stack, and especially in Sparkle? So first, one more reminder about the syntax of Turtle and Sparkle. X has value 42, Y has value 314E minus 2, and Z has value 3.14. What would be the data type of the value of X? Anybody? That would be X as the integer. I guess not much surprises here. The second value is of type double. The third value, on the other hand, is of type decimal. This is something in Turtle and in Sparkle, okay, which is, when you think about it, a little unusual in programming languages. Most programming languages do not make any distinction between 314 exponent minus 2 and 3.14. Okay, that in Java or JavaScript or Rust, that would be exactly the same value. In RDF, well, at least in Turtle and Sparkle, they represent slightly different things. And it's more than slightly, because remember, the value spaces are different. So those two things not only have different data types, but they actually denote different things in the universe. Well, although, again, this doesn't have much practical consequences, as we will see. So when it comes to comparing terms in Sparkle, we have basically two tools. We have the function sameTerm, which compares terms syntactically, meaning that, of course, any IRI is not the same term as any literal, and which also means that two literals are not the same term if they differ by their data type or if they differ by their lexical form, even if those lexical forms happen to be equivalent with respect to the data type, okay? Equal, the equal operator, on the other hand, compares terms based on equality. And equality here is inherited from, I think, the XPath specifications. And it's different from identity. So basically what it boils down to is that for numbers, even though one as a double is not the same resource as one as a decimal, they are still mathematically equal, according to Sparkle, okay? And what's important, what is one thing that I didn't quite realize until recently is that although RDF, as I said, any RDF complying implementation is only required to recognize two data types, strings and language strings. Sparkle, on the other hand, is much more demanding. Any Sparkle engine has to recognize a set of data types that include integer, decimal, and double, and also date time and a few others. Okay, and so any Sparkle engine is required to behave consistently when it comes to the equal operator, even across data types. Meaning that if we compare the integer one and the decimal one, or the integer one and the double one, or the decimal one and the integer one, if we compare them with same term and with equal, what should we get? And if we compare terms of the same type, so the 3 last lines, I realize that you don't see my pointer. Maybe what I should do is, when I select them, maybe that's better. Yeah, you can see the selection, right? Yeah, okay. So also, if I compare 2 integers with different lexical form, or 2 decimals with different lexical forms, and 2 doubles with different lexical forms, and I lost my window now. Okay, sorry. What should we see? That's what the specification, what the Sparkle specification says we should see. In all cases, the terms are not the same, syntactically speaking. Okay, and in all cases they are mathematically equal. Okay, so again, sorry. Again, the select selects x and y, then same term xy as same term, and x equals y as equal. So in all cases, the terms are distinct, either because they have different data types or because they have different lexical forms, even in the same data type, but they are all mathematically equal. That's the theoretical result. So I was curious and did the test with a number of Sparkle engines that I use on a regular basis. And this is what I got: Coriz, GraphDB, G9, Ruby Sparkle, and there's a bug here, but anyway, all give exactly the correct result. Oxygraph, which I don't know if I think I mentioned that earlier. Oxygraph is a very nice triple store coded in Rust by Thomas Pellissier-Tanon, which I encourage you to test if you're interested in Rust. RDFlib is the Python library for RDF, and Virtuoso doesn't need any introduction, I guess. They all behave slightly differently. So this is the result of Oxygraph. What can we see? We see that the lexical forms of the literals have not been preserved. Okay, and that's why, by the way, I add the actual data type as the exponent. So of course, the data types are preserved. That's the minimum. And the lexical form have not been preserved, even though they are semantically equivalent to the original one. And again, that's fortunate, otherwise that would be a huge bug. But then the results are not exactly the ones that we expected, because then the last 3 lines are reported as using the same terms, which was not the case in my query. Is this a bug? Is this a lack of compliance from Oxygraph? One might say that Oxygraph is complying with the Sparkle specification, but with a different part of the Sparkle specification, okay? Because Sparkle also has this notion of entailment regime. That is, you can query just the graph, and that's what the basic specification describes, or you can query the deductive closure of the graph for some form of inference. And basically, by normalizing the literals, I guess, as they are inserted in the graph, that's how I guess Oxygraph is working. By normalizing the literals, basically what Oxygraph is doing is de-entailment by default. Okay, and if we take this as Sparkle using the de-entailment regimes, recognizing x is the integer, x is the decimal, and x is the double, then that will be the correct result. So it is semantically okay, right? But the results are different from another Sparkle engine, which might be a problem in some cases. Basically, what RDFlib is doing is the same, except that the normalization is slightly different, as you can see, but the same term and equal columns are the same. And Virtuoso is also normalizing in a different way. An odd feature of Virtuoso also is that instead of returning booleans for safe term and equal, it returns integers. But that's Virtuoso, right? that's one thing to keep in mind when you use the Sparkle engine. You don't always get exactly the same results. Again, semantically, there's no that's valid semantically, but sometimes when you're using same term, obviously you're interested in more or less, depends how you look at it, than the semantics. Okay, when you use same term, it's that the syntax is somehow important to you. Then I had the idea of doing more comparison. So the first three pairs here compare three values that are very, very close to 0.1, either decimal here and there, or double here. When I say very, very close, it's they are closer than a difference that can be represented in XSD double. There is no limited precision in XSD decimal. Okay, I can make the decimal as long as I wish. That's part of the data type. On the other hand, XSD double is limited to 64 bits. So there is a precision limit. And as you might know, there actually this lexical form is the closest approximation of 0.1 that we can get from an XSD double, because 0.1, 1/10, cannot be accurately represented as a binary floating point number. And so basically no, sorry, I was going to say something that's probably wrong. So those two decimals are different as decimal, but they are close enough to this double that they should be considered equal. The last three pairs are very big numbers. Okay, 10 to the power of 22. Basically, that's more than a 64 integer can store. Okay, but again, the XSD integer data type is not limited in the number of digits. So I have two integers, 10 to the power of 22, and the same one plus 99, and then the same numbers represented as decimals and as doubles. So again, this is the nominal results, what a complying implementation should return. The two decimals are not, well, none of these pairs are with the same term. Okay, the terms are always syntactically different. Those two decimals are different because they have different lexical, well, they have different lexical forms, and it's not just a matter of leading zeros, so they represent different values. What might be surprising is that, again, when compared to the double, they're supposed to return equal. And it took me some time to check that that was indeed the correct result according to the specification. The reason is that when you compare a double to a decimal, you're supposed to upgrade the decimal to a double. And again, I think upgrading is the term in the XPath specification, or promoting. I don't know. Well, something that's strange, because by doing so you lose some precision. And one consequence is that the equal relationship in Sparkle is not transitive. Okay, you have those two things that are not equal together, but are both equal to a third value. That's a bit odd, right? Well, except when you're used to the double equal in JavaScript, but that's how Sparkle engines are expected to behave. For the big numbers, the two integers are not the same term and are mathematically different. The two decimals are mathematically different. The two doubles are mathematically equal, because actually the small difference, the 99 difference, is too small relatively to the number to be stored in the 64 bits. Again, a few tests. So GraphDB Gina and Ruby Sparkle passed the test. RDF-lib, Coriz, and Oxygraph, not quite, as we will see. And Virtuoso, well, we'll talk about Virtuoso. RDF-lib considers the value close to 0.1, all different from the XSD double. Honestly, I'm not shocked by this result personally. As I said, at least this keeps the equal relationship transitive. Well, that's not a proof, but so I don't know exactly. I didn't check how it is implemented. That's not what the standard says that it should return. For the rest, we don't have any issue. Queries. So my assumption, and some people here might confirm or infirm it, but my assumption is that queries converts decimal to doubles whenever it compares them. So that even those two very close decimals are reported as equal, while they should not. And also those two decimals that have a very relatively small difference between them are reported as equal. Those two integers, those two very big integers, are not reported as equal or not. It returns null. I'm assuming they are converted to native Java integers under the hood, and therefore, as it overflows, there might be an error. But again, that's just my assumption. Oxygraph is also strange. So we have something that probably reflects errors under the hood. The equal returns null in those cases. So same analysis for integers. I don't know what happens for decimals, honestly. And what's strange is that those that should be, so the decimal that is slightly below 0.1 is reported as equal. The one that's slightly above 0.1 is reported as not equal. But if we make it slightly closer, then it is reported as equal. And that's strange because even in, I tested in Rust, this value as a double is indeed equal to that value as a double. So I don't know exactly what happens. Virtuoso. So that's my Virtuoso bashing slide. Does really strange things. Still those integers instead of booleans. Here, so remember, here we had something slightly below 0.1 as a decimal and something slightly above 0.1 as a decimal. Both are reported as 0.1 in the result. So one might think they are normalized to something, maybe under the hood Virtuoso uses double, but actually those two identical terms, that they are decimals, both of them, are reported as not the same term and not equal. While clearly the ones returned, the value returned for X and Y are the same, are exactly the same. So I'm guessing Virtuoso is truncating the lexical form for some reason, but under the hood keeps a more accurate value.
Pierre-Antoine?
Yep.
You are positive on the typing, the data typing?
I am. I checked twice. So so I guess that Virtuoso returns trimmed versions or rounded versions of the values that it actually uses to compute the results. Then for 10 to the power of 22 and 10 to the power of 22 plus 99, this is what I get back. I gladly pay a couple of beers to anyone that can make any sense of those results. And in case you're wondering, the difference between the two is not even 99. And it's not the modulo of the actual value per 2 to the power of 64 or something like that. I really couldn't get any sense of it. So a few lessons learned. Oh my gosh, I really talk for too long, I'm sorry. Anyway, so the interoperability of type literals with Sparkle Engine is not as good as one might expect. Some Spark engines do simple entailment, some Spark engines do de-entailment, and that's not necessarily very well documented, or at least that's something that I would expect could be switched on and off. Okay, and no, they seem to have their default behavior. Dealing with arbitrary large numbers, and when I say large, I'm referring to the number of significant digits, not necessarily to the magnitude, can be tricky. Well, that's, I guess, any programmer would expect as soon as you go away from the charted territory of 64 integers and floating point numbers. But still, the data types are theoretically not limited to this. And I wanted to quote here, to cite here a very nice paper that was published in ESWC 2022 about the problem with XSD binary floating point data types in RDF. Basically, the author advocates for avoiding as much as possible those lossy data types, such as XSD double and all the more XSD float, in favor of unlossy, at least theoretically unlossy data types, such as XSD decimal. JSON-LD is also a source of interesting surprises when it comes to literals. So basically, to represent a literal in JSON-LD, the general way is to use what are called value objects. So that's a JSON object with two special properties: add value and add type. Okay, and that produces the following RDF. So property xFoo has value a literal whose lexical form is foo, and data type IRI is x bar. Okay. But JSON-LD also allows native JSON values. So if I put 42 as a number in JSON-LD, what I get is an RDF integer. Nothing very surprising here. If I put 42.1, what I get is a double, which might be a little more surprising when you're used to turtle, okay, because that would be a decimal, but that's not how JSON-LD is defined. But again, that's fair enough. That's how it works in many programming languages. However, if you put 42.0, you still get an integer. At least that's what the spec says. And I realized that PyLD, the Python implementation of JSON-LD, produces an XSD double instead, which is non-compliant. So the rationale is that most JSON-LD parsers are based on the standard JSON library under the hood, okay? And most JSON libraries do not give you access to the syntactic representation of the number in the JSON source, okay? They pass those into native numbers, native in the programming language that you're using. And therefore, you don't know if this thing was written 042 or 42. And as a matter of fact, in some languages such as JavaScript, which is obviously a reference language for JSON, you don't even know if it was 42 or 42.0, because JavaScript doesn't make any difference between integers and floating point numbers. It has one type, that is number, right? And therefore, JSON-LD is defined in such a way that you do not consider the type of the number to decide what the data type of the literal will be. You look at the value of the number. If the number has no fractional part, then it will be typed as XSD integer. If it has a non-zero fractional part, then it will be typed as a double, and that's it. There's actually slightly more to it, but I don't have the time. And I assume that PyLD is not doing that because Python makes a difference between integers and doubles. So this would be passed by the Python JSON library as a double, and then the developers of the JSON-LD library were too quick and serialized that as an RDF double. And of course, there's also a thing in JSON-LD called type coercion. And basically, it allows you to put in the context the information about the data type so that the data doesn't need to contain the data type every time. So basically I say X who is expecting XSD decimal. And then all I have to put in the data as the value is the string 42.1, and I will get the decimal 42.1 as the RDF. That's nice, but it has its caveats. What if I put the number of 42.1, which would be much more intuitive, right? That's a number in the end, regardless of the data type that I want in my RDF. Now, the problem is that the standard way RDF, JSON-LD will serialize that is with using the canonical form of the double, which is not a valid lexical form for decimal. So this would actually generate an inconsistent RDF graph because this decimal is not a valid one. It's just as bad as writing hello world of type decimal. So type coercion is nice, but it is tricky. And lessons learned, well, JSON-LD supports JSON native numbers, but the general advice is to not use them unless you're forced to. And that is unless you are using JSON-LD with a legacy JSON format that requires you to use numbers. And in that case, you can do more or less what you would expect with those numbers. But when you are designing a JSON-LD format from scratch, it's much more, it's much safer, more robust, and more flexible to use string plus type coercion. And even though this kind of thing is maybe less intuitive than that kind of thing, but at least it would give you the proper result. What about shackle? And as a matter of fact, the questions around shackle came from the discussion around JSON-LD, and so a little more context. This question about JSON-LD came up in the DCAT working group, where there was a question: what should be the data type for this property? And if we choose, for example, XSD decimal, what does that mean for JSON-LD context? And then we came up in this issue with the fact that we were generating ill-formed decimals if we were using numbers. So the idea was, could this be checked by shackle? And this is what we came up to. So here's a shape that should be satisfied by any instance of person. And if a person has an age, the age should be a non-negative integer. Sounds reasonable enough, okay? Nobody has a negative age. So then what happens with those instances? Okay, A has age 18 of type non-negative integer, B has type 19, C has type 20.0, which is a decimal, right? But which is also an integer. And finally, D has this ill-formed non-negative integer. Okay, that's actually the result with the shape. The first one passes, well, validates the shape. The next two do not validate the shape, while, well, we might wish them to validate that, because after all, that, again, sorry, I didn't mention that, but non-negative integer is derived from integer. Okay, the value space of non-negative integer is a subset of the value space of integer. So semantically speaking, this is a non-negative integer. This is this is denoting a non-negative integer. This is denoting a non-negative integer. But syntactically, obviously, this is something that shackle doesn't understand. What shackle doesn't understand also is that this thing is not denoting a non-negative integer. Okay, so syntactically, it has the correct data type. Okay, it passes. Maybe that's not what we want. So I'm not a shackle expert, okay, disclaimer, but that's how I managed to solve that, or solve that for those 4 examples at least. So the value should be one of those three things. It should be either with data type non-negative integer or decimal. That's all the super types of non-negative integer. I added this constraint, which might look redundant. Okay, if it's not non-negative, it is greater than or equal to 0. But actually, this is for preventing ill-formed literals. Okay, because anything that is not well-formed will not match the greater than or equal to 0. I could have used a pattern, for example, to solve that, but that was easier to write. If it's an integer, it must also be greater than or equal to 0. If it's a decimal, then it must match this particular regular expression. I couldn't find any simpler way to keep only those decimals that are positive and that have a 0 fractional part. And with this, I managed to get the expected result. But of course, that's still brittle. I could use yet another data type like byte. Okay, a byte is a number between 0 and 255. So that's a non-negative integer as well. And semantically, it is. The value space is a subset of the value space of non-negative integer. And yet that didn't pass until I had yet another special case in my shape. So what I find confusing with Shackle, and I know that a number of people in the team are working with Shackle, I would be happy to discuss that next time I come. But from the look of it, shape languages are about the syntax, but it's actually not as clear cut. Okay, and some constructs are purely syntactic, like sh data type, which really just look at the literal and say, okay, it has the correct data type on the face of it, okay, not semantically, but syntactically. Even if it's ill-formed, I don't care. That's the data type. And some of them are actually semantic aware, like mean inclusive is parsing the lexical form. And it is actually semantically aware, because if I put 42 as an excessive string, it does not report as mean inclusive 0. Okay, the string 42 cannot compare to 0. So there's really some semantics involved here. Shex does exactly the same, by the way. So, and again, it's what you would I guess that's what you would expect from a shape language. But what the take-home message for me is that the boundary between supposedly shapes that deal with syntax and ontologies that deal with semantics is not so clear-cut. Also, Shackle inherits a lot of things from Sparkle. That the spec is defined that way. Maybe that means that the interoperability problems that we saw with Sparkle could be also inherited for some Shackle implementations. Although I haven't found any examples where those issues would lead into validation issues. Literals in OWL. So OWL also is, any implementation of OWL is expected to recognize a lot of data types. There's a very long list, including all the variants of integers and decimals, like non-negative integers and so on. It also has its own data type, like OWL rational and OWL real. So here's an OWL axiom. Anything that has favorite number an integer, he's an integer lover. And Alice has favorite number 42 of type X as an integer. Bob has favorite number 1.0 of type X as the decimal. What we can infer is that both Bob and Alice are instances of integer lover. Okay, semantically, again, we are in the realm of semantics here. So as I already pointed out, well, this thing is obviously an integer. I mean, even syntactically, this thing is semantically an integer, even though syntactically it's an XSD decimal. Okay. And what we see is that Hermit, as deployed in Protege, is correctly inferring that Alice and Bob are integer lovers. Cories is only inferring it for Alice, and GraphDB with OWL in both. Well, in all cases, of course, I'm talking about queries and GraphDB with OWL RL activated. And yes, this is valid OWL RL. I checked that this meets the constraints on OWL axioms that the OWL RL profile has. And I, with the rule set for OWL, I is a notation 3 engine. And it has a number of rules for OWL RL. It doesn't infer any of those. So again, very quickly, it's interesting to see that inference on data types is obviously incomplete in some RL reasoners. One of the reasons is probably that the table I checked in the profile in the OWL profiles document, and there are a number of tables listing all the rules. Not all the rules. It's not claimed to be complete, but it's a non-normative list of rules that can be used to implement OWL RL on a rule-based engine. And some of them are about data types, but the problem is they are not very operational. They are, for example, the rule says there should be a conclusion that says X is of type DT for all X in the value space of the data type DT. So it's not easy to implement that efficiently and realistically. And also, because they produce generalized RDF with literals in the subject position, I guess that they are not always considered by implementers. But again, I'm happy to discuss that with the people behind Cores. Very quickly, two things that are in the pipes for literals. One of them is the base direction. So I said that I would briefly mention language tags. At the moment, RDF is able to attach a language to a string, but language is not always considered enough. Sometimes the base direction, that is it left to right or right to left, needs to be explicitly specified. And that's a requirement of the internationalization people at W3C for all new recommendation that deal with displayable text. And well, some literals in RDF are meant to be displayed to the user. And if we want to do that robustly, we need a way to convey not just the language, but also the base direction. JSON-LD 1.1 has introduced something like that, but at the moment, we don't have a standard way to convey that in the RDF graph. There are a few options, and of course, again, I'm going very quickly because we are at the top of the hour, but I'm happy to take questions after that, even offline. So those are two options that are suggested non-normatively in JSON-LD. None of them is current. Well, and the RDF Star working group, which will be publishing RDF 1.2, is currently considering making one solution standard so that RDF graph can contain displayable text with enough metadata to be correctly displayed in any language, any script, and any direction. And another thing that I wanted to mention is the proposal by Maxime Lefrançois and Antoine Zimmermann about a data type for representing physical quantities. So basically that looks like that. And I'll just leave this for you to ponder on and stop there anyway. That's all I had. Thank you very much. And I hope we still have some time for a few questions.
Thank you very much.